Here we're going to take a look at Young's modulus in a more numerical fashion. So we're now actually going to do a numerical example to get a better understanding of stress and strain in Young's modulus. Again, the definition of stress. Stress is simply equal to the ratio of force divided by area. And notice the units for that would be newtons per square meter. The strain is the ratio of the amount of deformation, how much the shape of the object changes relative to its original shape. In the case of a problem where we talk about the linear dimension only, it's the change in the length divided by the original length. And notice that both the change in length and length have as units meters. Meters divided by meters, the units cancel, so there's no units. So it's meters divided by meters, which is basically unitless, right? So the strain is a unitless concept. Now, if we take the ratio of those two, stress divided by strain, notice that would be newtons per square meter, or pascals, divided by no units. And so we know that the ratio of that in units is simply newtons per square meter, or pascals. And I use brackets to note that I'm talking about units here. And so therefore, since we know that stress divided by strain is equal to the Young's modulus then has units, newtons per square meter, or pascals. And just for reference, we put down some Young's moduli numbers for various materials: aluminum, brass, copper, glass, and so forth. Notice iron is a fairly strong material. It has a very high Young's modulus. And then something like lead, which most of us have experienced, lead tends to be a very soft metal. We can deform much easier. You can see that Young's modulus for lead is much, much smaller than Young's modulus for iron or nickel or steel. All right, so now let's do our problem. We have a beam made of iron. The length originally is 1.75 meters. The cross-sectional area of the beam is 2 centimeters by 2 centimeters. And the amount of force we're applying is 1,000 newtons. 1,000 newtons, that's roughly about, let's say, about 200 pounds or so. So how much will that beam shrink in size? How much will it be deformed under that kind of force? All right, let's find out. The stress divided by strain, which by definition is equal to force divided by area, and we divide it by the change in the length over the original length, and of course that's going to be equal to what we call Young's modulus. Now what we're looking for is the change in the length right here, so we have to take this equation and solve it for delta L. Notice this gets a little messy, so I'm going to clean it up a little bit. So we're going to write as force divided by area like that. And now we're dividing that by the fraction delta L over L sub naught. So whenever we're dividing by a fraction, that's the same as multiplying by its inverse. I'm going to multiply that times the inverse of the fraction, which is L sub naught divided by delta L, and that's equal to Young's modulus. Now, to separate the delta L, I'm going to move delta L to the other side. Remember, when we have a fraction equal to a fraction, we think of this as Young's modulus over 1. We go across diagonally. So what's in the denominator on the left side goes into the numerator on the right side, and what's in the numerator on the right side goes into the denominator on the left side. So this can now be written as, and I guess I don't need the equal sign there, so we can write this as force times length initial divided by the cross-section area times Young's modulus equals delta L. So we separated out the delta L, so I can bring that over here. Delta L is equal to force times the original length divided by the cross-section area times Young's modulus. And all we have to do now is plug in the numbers. So for the force, we have 1,000 newtons. The original length, 1.75 meters. Cross-sectional area, of course, we have to convert that to meters or square meters. So we have centimeters, convert to meters, that would be 0.02 meters. And of course, we have to square that because the area of a square is the side squared. And then we divide that by Young's modulus. Since we're dealing with iron, we're going to pull out Young's modulus right there, which is 21 times 10 to the 10th pascals or newtons per square meter. In just a moment, we're going to take a look at those Young's moduli and figure out what that really means. But first, let's find the solution to this problem. So we have 1,000 newtons times 1.75 divided by 0.02 squared and divide by 21 e to the 10th equals, and that's a pretty small number. That's equal to 2.08 times 10 to the minus 5. Of course, that would be in terms of meters, because we're looking for delta L, and that would be equal to 0.0208 millimeters. And of course, If you know what a millimeter is, that's a very small distance. And so you can see that even with a force of 200 pounds, a steel beam like this, that's 2 centimeters by 2 centimeters, that's less than an inch, 2 centimeters, you would not deform the beam very much in length. It would be a very, very small deformation in the length. So how do we look at these numbers here, Young's modulus? Again, the way to look at it is the amount of stress required to obtain a certain amount of strain, a certain amount of change in the length. For example, with iron, you would need a much greater force per unit area to deform something a certain amount than you would for the same size lead. You would need a lot less force per unit area to deform it the same amount. So it's kind of a number that gives you an indication of how much force per unit area you need to apply to obtain a certain change in the length. For example, how much force would you apply if you want a 1% change in the length of the beam? Let's do that. So here we can say, let's say that we want to change the length of the beam in such a way, so what would be the force required? F is equal to question mark to obtain a 1% change in the length, so that the ratio of delta L divided by L initial is equal to 0.01, which is 1%. How much force would that require? And so not to get us too confused here, let me find a different color to work with. So what we're going to do now is we're going to find the force. We're going to put everything else over to a different location. So we're going to put the delta L over here, the A over here, the L sub naught over here. So we can say that the force is equal to Young's modulus times the area times the delta L divided by, we want L sub naught on the denominator right here. Now realizing that delta L divided by L sub naught by definition is going to be 0.01. So let's plug in all these numbers, and again, let's assume we're dealing with an iron beam. Young's modulus, we have 21 times 10 to the 10th, and that would be pascals, or newtons per square meter. The cross-sectional area, okay, we know that's 0.02 meters, and we have to square that. The change in length divided by L is 0.01. Okay, so 21 e to the 10th times 0.02 squared and times 0.01 equals, and that would require 840,000 newtons. So that would be 840,000 newtons of force in order to compress the beam by 1%. So that would be 1.75 meters. So that would mean a compression of 1.75 centimeters, because centimeters is 1/100th of a meter. Wow, that would require 840,000 newtons. That's a lot of force. Another way to look at it is, notice that the units here are pascals, which are newtons per square meter. So let's assume now that we have a cross-sectional area of 1 square meter. So let's make a really big beam. So that's 1 meter by 1 meter. And we want to have a deformation of 1%. So let's say that the length of the beam, let's call it 1 meter beam, 1 meter long. And there it is. So that would be the original length. Still an iron beam, but now we have a cross-sectional area of 1 meter by 1 meter, 1 square meter. And we want the change in the length to be, again, 1%. So the delta L divided by L sub naught is equal to 1%, which is 0.01. Okay, now how much force would it take now to do that? And I think once we do that, you have a very good idea of how to look at these moduli. All right. Okay, again, we're going to take the force. So force is equal to Young's modulus times the area times delta L divided by L sub naught. But again, delta L divided by L sub naught is 1%. And notice that my cross-sectional area is now going to be 1 meter squared. So this is going to be, for iron, Young's modulus is going to be 21 times 10 to the 10th pascals, that's newtons per square meter, times 1 meter squared, times 0.01. So now that we kind of use a standard unit for cross-sectional area, 1 square meter, and we are looking for a deformation of 1% or 0.01, and that was the Young's modulus for iron, notice that then the result will be 21 times 10 to the 8 pascals. So now we have a pretty good idea that this kind of tells us the amount of force per unit area we have to apply to obtain a certain ratio of change. For example, if we want a 1% change, we multiply this by 1%, and that's the force per unit area you have to apply to gain that percent. If you want a 10% change, then you have 21 times 10 to the 9th newtons per square meter to deform a material. So now you can kind of see how that Young's modulus kind of plays hand in hand with the numbers you get for the force required to deform it a certain amount. Well, hopefully that'll give you some good feeling for what Young's modulus is, how we apply it, and how we can calculate the change in the length or perhaps the force required to gain a certain amount of deformation. That's Young's modulus.